Welcome. In this video we will cover the final part of chapter 13, where we discuss climate change.
Let's shift our attention to ozone. Ozone is an allotrope of oxygen because it has one extra O atom than oxygen gas. Ozone is produced in the troposphere, where the oxygen can combine to form the ozone, using the UV radiation from the sun. Inside the troposphere, ozone is a hazardous and toxic substance. It's one of the contributors to smog and indoor air pollution. However, once ozone travels into the stratosphere, it creates an important shield over Earth. This shield helps to preserve the temperature and life on Earth by preventing harmful ultraviolet radiation from entering into the troposphere. Let's take a look at the mechanism by which ozone is created. In the mesosphere, ultraviolet radiation can split the oxygen molecules into individual atoms. An oxygen molecule reacts with the energy from the UV radiation to produce two oxygen atoms. These oxygen atoms can then react with another molecule of oxygen to form an ozone molecule. One molecule of O2 reacts with one molecule of O to form ozone. Once the ozone is produced, it can trap UV radiation with the reverse reaction. The UV radiation breaks the bond within the ozone to form a molecule of O2 and a molecule of O. This chemistry is occurring consistently where the ozone and the oxygen are being converted back and forth within the atmosphere. While this reaction is occurring, it's trapping a large amount of the UV radiation before it's able to reach Earth's surface. Chlorofluorocarbons are molecules that used to be used as refrigerants and foaming agents. At this time, most of these chlorofluorocarbons have been banned from use because of the negative effects we're about to discuss. The chlorofluorocarbons, depicted here, one molecule CF2Cl2, can combine with the energy from the UV light to form free radicals. These free radicals can react with the ozone to decompose it and create oxygen. Once this reaction occurs, another molecule of radical is produced and then can go on to trap more of the ozone. This is a chain reaction that can occur, and it's extremely important that chlorofluorocarbons are not released into the atmosphere because they will slowly reduce the amount of ozone present in the atmosphere. One of the major problems with chlorofluorocarbons is their low molecular weight. For example, CF2Cl2 is a gas at room temperature. When an old refrigerator leaks any of this material into the atmosphere, it goes directly into the gas phase and is able to travel up into the stratosphere where it can disrupt the ozone layer. Most recently, refrigerators are made using different molecules that have a higher molecular weight. This prevents the coolants from going into the gas phase if the refrigerator is destroyed or the refrigerants are leaked. In this diagram, we can see the emergence of the ozone hole over Antarctica. This is the largest area on Earth that lacks in the ozone layer. The reason is because polar regions have a much larger variation in sunlight than anywhere else, spending almost 3 months in darkness during the winter and without solar radiation. This dry stratosphere is a perfect opportunity for the ozone layer to deplete. You can see in this diagram between 2000 and 2013 that the hole in the ozone layer over Antarctica is slowly increasing. Carbon dioxide is one of many greenhouse gases. Greenhouse gases have the ability to allow solar energy to penetrate the atmosphere but trap the heat in. The higher the concentration of greenhouse gases in the atmosphere, the more heat that's trapped into the Earth's atmosphere from the sun. Over the last few hundred years, with the Industrial Revolution and the burning of coal on a large level, human activity has contributed tremendous amounts to increasing the amount of carbon dioxide in the atmosphere. Here's a diagram that helps show this depiction. The energy from the sun passes through the atmosphere. Some of the sunlight is reflected by the ozone layer or other molecules in the atmosphere. The greenhouse gases help to trap some of the energy that's being lost into space as heat. Over time, the higher the concentration of the greenhouse gases in the atmosphere, the more energy from the sun that's being trapped onto the Earth's surface. Here is some data that shows the concentration of carbon dioxide in the atmosphere going back for 1,000 years. We can see that between year 1000 and 1750, the concentration of carbon dioxide is relatively stable, around 280 parts per million. Once the Industrial Revolution occurs, the concentration of carbon dioxide begins to increase at an alarmingly quick rate. Here's a blow-up between 1960 and 2000. We can see over this 40-year period, the concentration of carbon dioxide goes up almost 50 parts per million. Using ice core samples, data was extrapolated that looks at the carbon dioxide levels over the last million years. We can see that there is a correlation between the ice ages and the carbon dioxide concentration. Lower concentration of carbon dioxide is correlated with cooler temperatures on Earth. Over this 1 million year period, the largest concentration of carbon dioxide is roughly 300 parts per million. As of 2017, this number is at 405 parts per million. The global temperature has increased almost half of a degree since the 1970s. When this data is extrapolated into the future, a range of a 1 to 5 degree increase is estimated over the next 75 years.